So I'm Nazih Mechbal from aeronautics. I will just present you quickly the institution, and I'm the coordinator of Morpho project that I will present you. We are in the middle of the project, so some first results, and also the concept of this project that is from CINEA, agency. Okay, so just I'm full professor. I'm the head of this lab, which is from Arts et Métiers, which is the oldest, one of the oldest engineering school in France, founded by La Rochefoucauld, which was one of the general of Napoleon. And we are in the center of Paris. And this is in the center of Paris, and the lab is here. And this lab is okay. It's okay. The lab. So we are 200 people, and we are working from multi-scale approach, from materials to structures, to robotics, to robots, to process stuff like that. So with a big theme on simulation and model reduction. The team that is leading this project is DISCO, for Dynamic Structure and Systems, that we work on developing some new actuators based on polymer, active polymer, or to do some process monitoring or characterization, stuff like that. And we rely on some in-lab simulation tools, dynamic tools, which is this one, for example, SDT tools. So just to address a picture of the laboratory. So for Morpho, it's a 4-year project with 5 million euros. The challenge was to extend the industrial leadership through cost-effective and ecological manufacturing. This is from the call. And the proposed support the development of smart aeronautical. It's dedicated to aeronautical structures, especially fan blade. This is the proposition of Morpho. And to follow, to assess capabilities, cognitive capabilities, and optimize their manufacturing and life cycle management. So there is 10 partners from 6 EU countries, and we have some companies. We have end user is Safran Composite, and we have Fraunhofer. Some small dedicated specialized companies, synthesites, that develop some sensors typically for the RTM process. And we have University Delft and Patras. Well, you have all the members are here. For the goals, so what is the goals? Define, design, innovative, environmentally friendly materials to manufacture, to monitor, during service and recycle. This is important. During service and recycle of specific materials, which structures that are multifunctional and multi-materials. This is the core of this project, because we will rely on embedded sensors from the manufacturing to the disassembling and recycling. And we want to work on some standards, especially for the recycling with the laser, as we will show you later. But this is what we want to do. So what is the main objective? It's to monitor what we call the hybrid fan blades that are used in now all the engine of Safran. And here it's the blade. It's formed from a titanium core. This is what we call hybrid. And you have here the core. It's a 3D woven, because it's specific. It's 3D woven composite. So from this fan blade, we have the demonstrator. What we use is we call the FOD, Foreign Object Damage Panel, because the geometry and the CAD of this fan blade is confidential. So we cannot work on it. So they took a piece that is representative of what is a fan blade, and we work on this piece, which is called FOD panel structures. Okay, so the objective. First, digital industrialization. As I'm going to present you, the manufacturing is used the RTM process. So we are going to embed the real process with some additional sensors to optimize all the manufacturing. on the fly. This is important, on the fly. Second objective, it's about maintenance. So we want to do some health monitoring and to reduce at least 50% of turnaround time. And third objective is disassembling, because you have the hybrid structure. So you have the titanium and CRPP. So we want to disassemble and then to recycle the composite part. And the idea is to have 100% recovery of the CF contents, and then to use the epoxy resin in the process for the energy. So to have a virtual process, because you need a lot of energy to do this complete recycling of the composite fiber. First is design. So now, currently, for the design of this kind of fan blade, they do safe life design. So we have 5 to 10% of more materials of size, because they say when there is an impact, foreign impact, so it will be already safe, and after a certain number of hours of fly, it goes to be burned. This is how they use now. There is no recycling of this kind of structure. They leave, there is no maintenance. If there is something is not working, it's throughout. So now the idea is, by coming with some sensors, is to do some damage tolerant design, which will redesign all the structures more lighter and stuff like that. And the last objective is for standards, because there is no standards for this kind of structures, how to do maintenance, how to do recycling, stuff like that. Okay, so what is the concept of Morpho? Is to use something that I think now it's everyone use this kind of word, is to do a hybrid approach, using hybrid twins that merge digital data and physical data. We are going to use physical models to model everything, and then to fuse with some data coming from all the sensors that will be embedded in services. And to do that on the fly. So we have to do some model reduction to have something that can compute quickly, interact with the data that is measured on the live, and then to decide if it's okay, not okay. And you have all the cycles, so digital data, and then you will do some recycling, reuse, and go on the process. So this is the idea, is to do something that have the dashboard that's going to show you at any time what's happened inside the structures. So to have your twins that talk with the structure and adapt all the modelization online in services. So for manufacturing, this is the idea of cognitive paradigm. For the manufacturing, it's an RTM process. We embed the mold with some dedicated sensors, which are the dielectric sensors that measure the time of arrival of the resin, and we add on the 3D woven composite embedded FBG sensors. I will show you how we do it. So for the dedicated RTM sensors, the Synthesite's partner developed dedicated sensors that measure the time of arrival of the resin. It's something that it's done for the RTM process. It's specified for the RTM process. It can be in RTM process. With these sensors, you can measure the time of arrival of the resin, and then you can optimize the pressure, the temperature online. For the fiber optic, for FBG, so it's a little bit tricky because it's 3D woven. It's not something that we put in a normal composite. So there is here you have a network of FBG that have been weaved into the 3D woven. So I can show you here how this is manually the first time. For the first time, it's manually. It's done manually, inch by inch. It's because it's 3D woven composite fiber. So it's like we are doing some, we are weaving coats. It's really the same thing. We can see the video here, I think. So it's done by a needle, and then the fiber enters the needle, and it's like my grandmother doing some. So it's done manually like that. To have, then here you have the results of the fiber by the light that you can see that it's completely embedded in this 3D, because it's, as you see here, it's really it's different. It's 3D composite, something that have been weaved before. So it's very time-consuming, but because it's the first time that we are experimenting that, then we think that we can automatically do it after with this, because here with the machine that is we do some 3D wovens automatically. So this is for the fiber optics that is embedded inside the structures in 3D woven composite fiber. And the idea at the end is to have a hybrid platform, hybrid twin platform, that will manage all this information coming from all the sensors and compare or rely on physical models, because data without some physical informations or comprehension of what's happened, it's nothing. And then this data-driven online learning is added to all the physical digital twin models that we have developed. And then we do some hybrid twin, because the concept of hybrid twin is not just to fuse, it's just the idea is not to use artificial intelligence for using artificial intelligence, because something now we use artificial intelligence for just using artificial intelligence. Here we use artificial intelligence just to modelize the ignorance, the difference between what we measured and what we predict with our models. Just this difference that has been, we use some AI just to model this difference, and we have, because we use some model reduction, because the idea is very important to know, we have some physical models, complete physical models, that is impossible to have it online, on the fly, to control, to monitor, to adapt what we are doing. So we go from that with some model reduction approach. And then with this model reduction approach, we can embed an online simulator. And when we measure something, if there is some difference, we use some artificial intelligence that from this difference to compensate the error that can happen between our model reduction, reduced model, easy to implement, very quick. And this is the idea of this hybrid approach. So this will be done for the manufacturing and for the health monitoring assessment during all the life, and for the recycling. So just quickly, without going through to the equations, this is just for the RTM. We use some here approach for the reduced model. It's the PGD, proper general decomposition, where it's based on the idea of separation, time, and space, and it's easy then to do some model reduction. And from that, we can, here, for example, we have an example of model simulation. If you use the real result, here is the front wave of the pressure of the resin. And if you go back just to see what's happened, if you model with the complete, if you have all the information and the real-time measure, this is what happened. This is if you use a virtual twin just to model with the equations or the information, but as there is always some differences, you will have some error. So with the hybrid twin, we'll compensate this error using some artificial intelligence. Okay, so this has been used in real time, also to identify why we use that, because with this, how I can say, reduced model quickly computed, we can make some online identification of some physical parameter. So here, if you can see, you have some data. This is the region that is coming, and the sensors measure the time of arrival of this resin, And here you have to adapt inline the identification of some physical parameter as permeability or running time. And this make the optimization online of the RTM process. Then you can make more pressure, stop, more temperature, adapt if you want. Okay, so this is the part of manufacturing. Now, assessment of during all the life. So this is the structural health monitoring. I know that, I think that anyone is, we are all, if you are not familiar with this system, structural health monitoring, it's just to go from intelligent maintenance, so to have the, not too early, not too late, to detect the damage, to quantify its severity. And it goes from something that will to conditional-based maintenance. So with the embedded structure, we can do maintenance when it's necessary, not when just a scheduled one, especially for aeronautic plane. Which after a certain number of hours of flight, it goes to be inspected. Now it will be inspected if needed. This is what we call the conditional-based maintenance. So, and the idea is to estimate this severity, then you can adapt your maintenance policy. So there is two ways to do it, passive or active. Passive, you sensors are only measuring what's happened, and then you decide. Active, these sensors can be used also as an actuator, dedicated for PZT, and then you inject some waves, and then you see what's going inside. So there is some steps: we detect, localize, estimate, predict. And this can be done online if needed. So we need more sensors to do that. So we have now FBGs that was used for estimating, for optimization manufacturing, but they will be also used for structural health monitoring, because they will have an information during all the life of the use in service of the structure. But more than that, we come with some we decide to add some more sensors. So we print some sensors. This is, you have piezoelectric, temperature, strain gauge, conductive line, have been printed on the structure. You have here some samples. This work is ongoing. And with these printed sensors, we can use them with the FBG to have all the information, necessary information during in-service structure. As it's printed sensors, there is no problem of wires, because it's a problem. I will show you an example of something that we did before. So the printed sensors here, you have, this is the colleague from IFAM that work on that. So we can print like a 3D printer, different type of sensors. And now we are managing to how to all this information can be used and to do some structural health monitoring. Okay, so for this we can use some algorithm. We have an experience to do some prognostic, because the idea is to have prognostic on the severity of the damage. Okay, if you said to a guy from MRO of aeronautic, you have to stop the engine because there is possibly a damage, he will not trust you more. You have to say that there is a damage, but there is no damage. If there is a damage, what is its severity? 10%, 20% damage, it's critical, not critical. So we have all a work package dedicated to how we can have all this information about the propagation of the damage, because it's very complex structure with this 3D woven, because you can have some delamination, but you can have also some kiss bonding. You have lots of phenomena that can be can be estimated as a damage, but it's not a damage. So we have a bench here that we use some fatigue tests, extremely fatigue tests, to have information about how the propagation of damage can happen in this kind of structure. With that, we will do some model inverse modeling with the aid also with some artificial intelligence to have some information about the remaining user life of a structure. Based on that, we can do complete structural health monitoring system. we have some experience. We have some experience. I have some experience on that because this is just inside. This is a national project that we finished before Morpho. It had good until TL5. And here, the sensors were glued on a nacelle of A380 that flew for 4 months, no crashing. And, and you have here all the problem that we had just with wiring. Just with wiring. This is what with printed circuit sensors, there is no problem of wiring. All the problem here is the wire that goes. Here there are 50 PZT sensors, and you have all the wires that go with. It's something very complicated. So here, the test of circuitical health monitoring, as you see here, it's a probabilistic approach. So it gives you the probability of to localize the test, to localize the damage, has been done on the ground. Because if you do it on the fly, you need certification that you will have never, you can finish the project before having the certification. So with this experience, she helps us to more design our sensors, how we optimize their placement, and we go out of this problem of wiring because it's really a big problem in this kind of approach. So I will not give you more information because it's confidential what's happened during the format, but you can always take the plane. It's safe. Okay, for the assembly. So we do health monitoring. Now we have to disassemble to recycle. This is two-way. The first way, not two-way. This is two stage. First stage is to use something that can disassemble the titanium from the CRFP. So for that, we are going to do some laser shock dismantling. And then we are using periodies to recover the fiber and to recover the fiber 100%. So for the dismantling, we have some facilities at the lab. It's a process, it's not something unique, but so we use laser shock. It's a high energy, high power laser in a very quick time. This laser shock will create interaction with the structure. You have a sacrificial stuff that we add here that creates thermal waves. These thermal waves will be concentrated in a layer of the structure. With the laser, so we can control, we can generate any delamination in a composite, in any layers, for controlled size. Here you have some example. You have 8 layers of composite. With the laser shock, we can delaminate the 3rd layer or the 5th layer, and we can create sizes that is being controlled. Using this system, we can dismantle the metallic part, the titanium part from the composite. And then this composite part goes to the partner who used that, it's Comet from Belgium, and using a pyrolysis, optimized pyrolysis oxidation propose, we can recover all the fiber. This fiber has been recovered, and now it's used to do some non-structural parts as the dashboard of the cars. We can reuse this fiber, something not structural, because you lose a lot of mechanical property. But you can use it also to do some dashboard of cars, stuff like that. During this process, the sensors that are embedded into the structure help the laser, help the process of laser dismantling to be optimized. Because when you do some shock laser, we have no information what's happened in it. But with the sensors that are in it, we can, this is a shock wave. We measure this wave, and then we can inline this. It's like a damage. Decide if the damage is very small or is growing, so we can optimize dismantling without not destroying all the structure. So this is we are at the middle because we have the COVID. So we should be more on this project, but with the COVID, we got some problem with the saffron, because saffron composite had a lot of problem with the COVID. And we hope that we'll have a demonstrator in 1 year and a half that will be this foot panel completely instrumented and an event test with simulating the rotation of the engine and having online recycling and online structural health monitoring. Thank you.
Thank you for your presentation. Very, very inspiring. I was just thinking about the sensors. How sensitive or resilient are they within the composite material? Because I expect that when you're doing monitoring, you can actually know when one's failing, but is there a certain minimum level of failure before you don't get good high quality results back? Or can you replace or repair the sensors?
Because it's printed, it's very easy to print. You print 1, you can print 10. And then you can some redundancy.
So the weaving, I mean, you said that was very slow. That was clear to see, and I guess there's some kind of scaling up to do here.
Yes.
Well, how is that envisioned?
They work with saffron that have all the weaving machine to see how we can go from this manually very delicate to the automatic to automate the stuff. Yes, they are working directly with saffron composite to do that. But this is not easy stuff. Just to win the first results.
And then we have been having it's called nano here and so on.
Yes.
So what is the size of these sensors that you're working with right now?
With the printed one, is we can do for the PZT it's 5 millimeters, and then more smaller as the temperature sensors. It's 1 or 2 millimeters. But then it's but you are not in nano, so if you can, we're going to put more. But yes, we can do more different sensors like that. But it's easy to certificate because you print on the structure, and you add no mass, and you mechanically you don't have to recertificate your structure. This is the problem with the aeronautical. If you put some sensors in it, the fiber, because it's weaved, it's okay because mechanically it doesn't change anything. It's, we have to deal with some constraint coming from the certification of aeronautical.
Yeah, no, thanks. This was really great. Thank you again.
Thank you.